Can everybody hear me? Great. So I'm going to talk about decoupled classifiers for group fair and efficient ML, and this is joint work with Cynthia Dwork, who's in the audience, Adam Tauman Kalai at Microsoft Research, and Max Leiserson at University of Maryland. So as we've been talking about throughout this conference, classification algorithms are increasingly used to make decisions of social consequence. So for example, you might have an automated resume reader that's trying to classify applicants using their features into positive, that is, someone that might excel at the job, and negative, that is, someone who might fail at the job. And so you could maybe do this classification using, for example, a decision tree of bounded depth, as in this picture, and you have the decision tree classifying applicants, and here you see that the true label of the applicant, represented with the minus sign attached to the figure, was negative, and the classifier classified the applicant as negative. And here you have an applicant whose true label was positive, and the classifier classified that applicant as positive. So for these algorithms to be useful, researchers and practitioners have strived to maximize their accuracy by minimizing some sort of function of the false negatives and the false positives. So here, for example, this classifier got most of the labels correct. It got most of the true positives it labeled as positives, most of the true negatives it labeled as negatives, but it had a few false positives and false negatives. Now, assume for a moment that the work environment itself is unbiased, such that equally qualified minority and majority applicants have equal probabilities of success in the job. Then, unfortunately, even in these situations, classifiers can result in unfair outcomes for minority applicants. Because, for example, maybe they will make all of their errors on the minority applicants. So here, for example, I've represented the majority applicants in yellow and the minority applicants in gray, and you can see that all the errors of this classifier are, in fact, on the minority applicants. This might happen, for example, in a decision tree of depth 1 if there's a single feature of the applicant that is perfectly predictive for the majority class and anti-correlated with success in the minority class. So here, for example, you have one feature, say a score on an exam, and it perfectly predicts performance for the majority class. That is, there is a single cutoff such that everybody to the right of the cutoff is negative and everybody to the left is positive. But it's anti-correlated with the true labels of the minority class. So in such settings, a classifier that is blind to the majority-minority label of the applicants has little chance of circumventing this problem. This raises an important question, which is, should a classifier use sensitive attributes in fair classification tasks? This is a very important question that this community has struggled with a lot over the years, and we do not answer this question. The answer is honestly probably application-specific, culturally specific, and may be legally mandated in one way or another, depending on the setting. Instead, what we look at in this paper is, supposing that you are allowed to use the sensitive attributes in the classification task, then how should you do so? So the proposal we have in this paper is that you should do this through the use of decoupling your classifiers. That is, you should train a separate classifier for the majority group, or you could have multiple groups, train a separate classifier for each group. So you have a separate classifier for the majority group in the running example in this talk, and a separate classifier for the minority group. This would allow us to perfectly classify all the applicants based on their score in the example we saw previously, because the feature actually perfectly predicts success for both groups. It just does it in a different way. And in fact, with a higher dimensional feature space, you can see that allowing decoupling can improve the accuracy for both the groups simultaneously. However, your classifiers still might be forced to make some errors, even when they're decoupled. And now this is going to force the decision maker to choose between accuracy trade-offs and fairness trade-offs. So you might want to choose a less accurate classifier for the majority class in order to help you achieve an equal odds type of outcome. And so, similar to the previous talk, we take the stance that you should consider the trade-offs, that I was really interested in the point that the speaker made, that at the end of the day, you are making some sort of trade-off. You are coming up with a decision, and that fundamentally has a trade-off between the utility and the fairness, or in our language, the accuracy and the fairness of your decision. And if you, as a decision maker, can specify that trade-off, then you can explore the optimal decision given that particular trade-off. So we take this stance as well, and we ask the decision maker to specify their trade-off in what we call a joint loss function. Now, the types of trade-offs we might be interested in are ones that can be characterized by statistics of the classifiers themselves. In particular, if you have attended the talk on 21 definitions of fairness yesterday, they were talking about false positives and false negative rates, and being able to express many notions of fairness using those false positive and false negative rates. Equivalently, you could use the error rate of the classifier, which is the fraction of the population on which it makes errors. So here you see my majority classifier classified 10 applicants and made errors on 2 of the 10 applicants for an error rate of 1/5. And the fraction of positives. So here my classifier classified 4 of the 10 applicants as positive for a positive rate of 2/5. And a lot of the fairness notions we know and love can be expressed as combinations of the error rate and the positive rates, as well as the accuracy notions that we know and love, which is just the total error rate. So as an example, here is balanced loss. In balanced loss, you want to minimize the average error, maybe weighted equally between the multiple groups in your setting. So the formula for this would be half the error rate on the majority group plus half the error rate on the minority group. And this balanced loss function might be what you want to minimize in order to achieve a fair classifier. Another example would be demographic parity, where you want to equalize the fraction of positives from the 2 groups. And again, you can write this using the statistics that I mentioned previously as the absolute value of the difference between the positives on the minority group and majority group. Finally, the third example I have here is a type of equal odds classifier. So here, the first term is the term with the 3/4 factor, is the total error on all the population. That's the total error rate. And that's sort of like the accuracy term. So you might want to take some combination of the accuracy and fairness, and here I've specified the trade-off between accuracy and fairness to be 3/4, 1/4. And the fairness term, the 1/4 term, is going to try to equalize the error rates across the 2 populations. So this is a type of equal odds that mixes in some proportion of accuracy into the objective function. And this is an example of a joint loss that combines fairness and accuracy. So in general, we're going to give a method for optimizing joint loss through decoupled classifiers. And it's going to work for any joint loss function that satisfies this property that I call monotonicity. So this is a somewhat technical property, but intuitively, it's asking that for your joint loss function, if you hold everything fixed, hold all the fractions of positives fixed, hold the error rates fixed for all the groups, and you take just one group and you improve that one group's error rate, so you get more accurate on one group without changing anything else about the outcome, then your joint loss function should only improve. So it's monotonic in the error rate for this one group. Interestingly, not all of the fairness notions we consider are monotonic in this sense. So for example, the equal odds that I discussed in the last slide, if all you cared about was equalizing the error rates on the majority and minority groups, you might, the best classifier for the minority group made some high fraction of errors, in order to equalize the odds, you might have to increase the errors on the majority group. That would be not monotonic. and our methods would not apply to that. The reason that I had to mix in some degree of accuracy is because by mixing in some degree of accuracy, I in fact monotonize the equal odds condition, which is a nice subtle point, I think. So the takeaway from this slide is that I can, our methods apply to joint loss functions that are monotonic in this sense. And they work through the use of what we call a reduction. So typically, practitioners will have access to some learning algorithm that takes in labeled examples that they use to train their classifiers. And these learning algorithms will take in some labeled examples and output, say in this case, a set of decision trees. And they will tend to output multiple decision trees, one for each target of false positive. One for each target of positive rate. So here we have 7 people in our population, so we're going to get one decision tree which has 1/7 of the population being identified as positive, and it's going to find the decision tree that minimizes the error subject to 1/7 of the population being positive. And then it'll also output a decision tree that minimizes error subject to 2/7 of the population being positive, and so on. Many off-the-shelf classifiers, in fact, learning algorithms, in fact, already output a suite of classifiers with this property, but if your favorite one does not, you can sort of massage it into doing so by upweighting different examples. So given access to such an off-the-shelf learning algorithm that trains your classifiers, we're able to call it in order to minimize the joint loss. And this is our algorithm which does that. It first trains the classifier on the majority group to get all the different potential positives and the minimum error rate for each of them. It then trains the classifier on the minority group, again getting a profile of all the potential positive rates and the minimum error for each of them. And then it just selects the set of classifiers, the decoupled classifiers, one for the majority and one for the minority, that minimizes the joint loss function that you've defined. So we ran our our algorithm in some synthetic experiments. Here we downloaded 47 data sets from openml.org, and we decided to select the first binary feature as the sensitive attribute. We then trained trained 3 different classifiers on these data sets. The blind loss classifier does not use this designated sensitive attribute. The coupled loss is the best classifier. In our case, we were using least squares linear regression, so it's the best least squares linear regression that uses this sensitive attribute. And decoupled is the algorithm I described in the previous slide. So each point is a data set, and the points that are below and to the right of the yellow lines, these are the horizontal and vertical lines in the graph, are points where coupled and decoupled loss are doing better than blind loss, as you would expect. And the points above the orange diagonal are the points where decoupled loss is doing better than coupled loss. We also trained a classifier on an anecdotal example, which was pictures of men, women, and people in suits from ImageNet. And we defined positive examples to be people in suits. And then we looked at gender as the sensitive attribute. And so what you can see here is that when we were trying to, this classifier was just looking at accuracy as the joint loss function. The previous one was doing balanced loss. But what you can see here is that by decoupling, or the coupled classifier, let's start with the one on the left, found examples labeled as positive, examples of women in suits that had more traditional male characteristics. The suits had a more traditional male characteristic. So tuxedo here versus the decoupled classifier, which labeled as a high probability of a woman in a suit, women with suits that were more traditional feminine styles. So to wrap up, the main takeaway is that decoupling classifiers, that is training a separate classifier for each group, can outperform the optimal single classifier in both accuracy and fairness metrics, which you can specify in an arbitrary trade-off joint loss function, so long as you satisfy this monotonicity condition. And this can be done in a black box manner, and this is one of the things that I like best about this paper, is that we're really just, our algorithm just calls in a black box manner an off-the-shelf learning algorithm to train your classifier, and therefore it can really be used by practitioners with their existing software toolkits. So the caveats to this work are that we require this monotonic condition on the joint loss function, and also, I didn't really emphasize this, but of course, since we're using decoupled classifiers, we need you to use the sensitive attribute both to train the classifier as well as to label data points as in our prediction step when they come into our system. So in some upcoming work, we're able to relax these conditions. Thank you. I'd like to call Cynthia up to join me for questions in case you'd like to ask her questions as well. Yeah?
Thank you for the talk. I loved it because it's an idea I played with myself, and yeah, I also saw that you can get high accuracy and you can get fairness. I came with an example that actually a little bothers me, and this is why I didn't go further with this. I want to describe it and hear what you think about it. What happens if the policy of a company is to hire men based on brain and female based on looks? And you'll end up with a good model which is fair, hiring the same number of female, same number of male, but it looks that it's not really fair. Not so pretty women cannot get to, the application will not be successful just because, even if they try very hard in school.
Sure, you want to?
I have no idea what the right answer to that question is. One of the things that we said in the paper was we actually envisioned, and this is not a really thought out answer to the scenario that you've described, but we actually envisioned maybe a more social setting and not such a professional one, where the members of the groups would say, we want you to use this classifier for us because we think this predicts best. So, you know, maybe there's some setting in which this is a good answer to your question.
Okay.
Thanks for the paper. I think it's really interesting because also a lot of literature on diversity emphasizes that different communities experience phenomena in different ways, and therefore modeling those might be important. I was wondering if you had thought about how this interplays with accountability. So if you are modeling phenomena it's a bit linked to the previous question, modeling phenomena in different ways, how might you communicate that to different groups, and what challenges might that pose in relation to other research presented here and elsewhere?
Yeah, so we were a little concerned that, you know, you might have a woman that performs well on some test that if she were a man, she would have gotten the job. But because she's a woman, she's judged according to different metrics and therefore is rejected from the job. So we played around with the idea of allowing the minority group to be positively classified according to either classifier. This, you know, of course, then causes the decision maker to make a call about who they want to treat preferentially. But that is something we thought of.
Thanks.